Hi, everybody. Welcome to our next round of Fellows Talks. We have four talks today. First up is Jordan. Jordan, you want to go ahead and share your screen?
Yeah. Okie dokie. Let's see here. Oops. I can reset my slideshow real quick. Okay. Awesome. Okie dokie. So hi, I am Jordan. I am an undergraduate at the University of Tennessee in Knoxville. I had the pleasure of working on the Repackaging Jet Substructure Observable Tools project under the expert guidance and infinite patience of Dr. Matthew Feichert of the University of Wisconsin-Madison and Dr. Henry Schreiner of the Princeton University. Just as a disclaimer, I am not going to try to explain what a jet substructure observable is. I do not know. They sound really cool. I would love to find out more at some other point, but if you ask me questions, I'm not going to know the answer. Um, I'm also not going to spend a whole lot of time on the tools themselves. I'm going to focus more in this presentation on what I did over the summer, which was repackaging these tools. But before I even get to that, a fair question to ask would be, what is packaging? Um, and there is a dictionary definition answer that I can give you. Bundling libraries, modules, or applications with, in theory, all the necessary dependencies, metadata, and documentation that that the software would need to function. To give you an example, though, let's say that I'm working on a research project with Zoe in Austria. And I tell Zoe, hey, check out this really nifty pure Python package called Energy Flow. All Zoe has to do, since Energy Flow is packaged, is do pip install Energy Flow. And what this does is it distributes the Energy Flow package directly to Zoe, installing it directly from the Python package index. So that is portable. The package is distributable, it's installable. It's also traceable. Whenever Zoe installs that, it does come from PyPy, the Python package index, which has the metadata associated with the package. So the author's name and all of the hard work in the documentation, the documentation that has all of the hard work that that author put into the package. So the best part, in my opinion, though, is just how efficient it is. With one line, you get all of those dependencies, you get all of that metadata. And looking at it this way, it's really easy to see that it's packaging is just good for science. Um, Now, what packaging doesn't do is it doesn't make your code static, which brings up the question, what happens when packages get old? Um, and that's where I came in, this project came in. Repackaging code is necessary, mostly because this packaging, any packaging installs dependencies. And those dependencies are not themselves static either. They change. The world changes around these packages. Um, so the dependencies themselves get upgrades and fixes. Hardware that we use also gets upgrades, and that can change compatibilities drastically in some cases. Looking at you, Apple. Also, the basic computing logic that the code is based on can change. We ran into a very interesting problem where over time, Windows implemented upgrades that changed how global variables were handled. Um, Whenever these changes are implemented and the code breaks, it can look very, very different depending on what's going on. So sometimes nothing works, which is fun. Sometimes some things work. And normally that's either certain platforms will work or only parts of the package will function properly. The scary part, though, is whenever everything looks like it works, your code builds, everything compiles, but your tests fail. And this is why tests are very, very important, especially with large, complicated packages. I had the pleasure of experiencing all of these things over the summer. And Um, I, I'm lazy. I really appreciated the opportunity to allow future maintainers of this project to be lazy as well. So we spent a lot of time on CI/CD for both of these packages, continuous integration, continuous distribution, and we automated as much as possible using GitHub Actions to enable that laziness. Um, so the incompatibilities that I mentioned earlier were also a major part of this. Apple Silicon and ARM were breaking our some of our builds, and also whenever I think of a stable Python package, something that is super reliable, just never changes, I think of NumPy. NumPy released its first major update in 18 years, NumPy 2.0. And for a while there, everything was broken and it was very scary. um, Downstream changes were implemented and everything is fine now, but that was definitely an educational experience. Um, the rest of the project focused on transitioning our build tools from something called setup tools to modern build tools, and that was different depending on the package. Setup tools is widely compatible, but it is also delicate and a little tedious. We moved to the more robust, for Wasserstein, we used Scikit Build Core, which is developed by Henry and is a beautiful modern build tool. And Hatchling was also used for energy flow. Hatchling works with pure Python packages and is also beautifully simple. Part of that process also helped us to figure out some other problems in the code. Minor things like fixes that were implemented that took some shortcuts that didn't quite work anymore, and bad links that were distributed throughout the code. And overall, I'm extraordinarily proud of myself and proud of Henry and Matthew. We did a fantastic job. And joking aside, I am honored and delighted to have been able to work on this project. The work that IRIS-HEP does is incredibly important, and it takes tools like Wasserstein and Energy Flow, the two packages that I worked on, and makes them accessible. And honestly, the products from these packages is just beautiful. Wasserstein takes extraordinarily complicated math and does most of it for you. I'm not great at math. I really appreciate that. The Wasserstein distance that this calculates is kind of animated here in this really nifty visual that is from the Energy Flow website. So it uses Wasserstein to calculate this distance, and then Energy Flow creates the visuals. But this is kind of a visual explanation of what that distance is. To give the best explanation that I can, it is the energy required to move from one probability distribution to another. So moving between these little circles, each one representing a particular probability distribution. Energy flow itself, beyond just creating beautiful visuals, also enables early data access and machine learning integration that makes our work just so much more efficient. Both of these tools were originally built for jet substructure observable research, which again, I don't really know much about, but they proved to be, oh, sorry, I forgot I had that in there. Yeah. They proved to be more widely compatible, widely applicable in both theory and experiment. And due to, again, the patience and expertise of Henry and Matthew and my time investments over the summer, I am delighted to announce that sometime over the next couple of weeks, we will be able to say you can pip install either of these projects. So coming soon. And I wanted to thank everyone so much for this opportunity and for your time. Thank you.
And I just wanted to jump in to say that Jordan really did an amazing job here. It was super impressive to see them be able to, start from learning the fundamentals of version control and then basically within just an incredibly short time span operating at the level of a like full package maintainer. So yeah, as was just mentioned, once there's some final approvals done, the revised versions and repackaged versions of Wasserstein and Energy Flow will be available across your favorite package indexes, but that's really all thanks to their hard work this summer. So it's incredibly impressive work by a university student in a short period of time. So thank you very much, Jordan.
Absolute pleasure.
Thank you, Jordan. Thank you, Matthew. Any questions for Jordan? No questions? Nice talk. Thank you, Jordan.
Hello, my name is Mykhailo Varvarin. I am a second-year master student of applied physics in Kyiv Academic University, Ukraine. And the topic of my fellowship was extending the Alpaka performance portability library with CUDA Cooperative Groups for the CMS pixel reconstruction. My mentors were Yizhi Vyskochil from Kazus in Görlitz, Germany, and Volodymyr Bezgubov from Kyiv Academic University. First of all, what is Alpaka, where it is needed? If you want to write a multi-threaded application for some computations, scientific or otherwise, you go basically over a few layers of abstraction. First of all, there are accelerators, either GPU or CPU, depending on what you have. And you have various APIs that enable you to run, to write multi-threaded software, which for the CPUs, they are more or less standard work over all vendors like OpenMP, like C++ std threads. But unfortunately for GPUs, each vendor has their own API. So CUDA for NVIDIA, ROCm for AMD, and one API for Intel. That's unfortunate because if you have to know and write in very different APIs. If you, for example, want to have compatibility with different GPUs, or maybe you have a few different GPUs on your cluster, and you want to load some part of your work on some of them and some on the others. Maybe you want to offload something even on a CPU, and these are all different APIs with slightly different approaches to things. Alpaka is basically an intermediary library, which allows you to write a single kernel function for your multi-threaded computations, and then it just on compile time, you specify which accelerators you want. Do you want CUDA? Do you want OpenMP or whatever? And it just compiles as if it was native code, which is very nice. And then it can be used by various applications. One application that use Alpaka is CMS Pata track that is used to I'm actually not entirely sure. It's somehow used to process data from the CMS in the Large Hadron Collider. Alpaka is a header-only library. It uses C++17, pretty modern, a lot of modern features with templates and a lot of compile time stuff that those templates enable. It supports all of those APIs. And it's thanks to use of templates, runtime performance is pretty close to just writing native code. What are cooperative groups? Why they're needed? Historically, on CUDA, if you wanted to synchronize your threads, so like guarantee that all the threads computed what they needed to compute on that step, and that the other threads can rely on what they computed. So, for example, if you, like, I don't know, calculating some heat equation, and you calculated each thread is a single point, and then you calculate step by step how the temperature changes. So the other threads need to guarantee that all of their neighbors completed their computation, and they can just get the data and calculate the temperature differences and proceed with their computations. For that, you use thread synchronization. Unfortunately, historically, CUDA only had thread synchronization on the level of a single block. That's up to 1024 threads, and the biggest problem is that the blocks are only computed on a single streaming multiprocessor of a GPU, and like consumer GPUs have dozens of them. Like huge accelerators have up to hundreds, and that's a big problem because you are leaving a lot of performance if you just use block synchronization. The other thing you can use, you can just thread each step of your algorithm just as a new function. So you load the function, it computes, and it returns its values, and then the next function is loaded, but it has a large performance penalty because all the sending data over the PCI Express bus to the CPU, and the invalidation of cache, and so on and so forth. And cooperative groups are a new abstraction that adds support for a bunch of different ways to synchronize threads. On a sub-block level, for example, just divide all of your threads into 32 thread-sized chunks and synchronize only within those chunks. Or you can synchronize the whole grid, and then you don't need to do all of this function loading and unloading. What was my task?
You muted yourself, friend.
Oh, sorry. So my tasks were, first of all, to research the way the Alpaka and CUDA APIs work, and come up with ways to integrate this functionality into Alpaka. The next thing was to create and and decide on exactly which parts were in the priority. Then to implement this functionality with CUDA, and then do the same with all the other APIs, with all their different quirks and strange behaviors. And as an optional task, integrate the functionality into the CMS pixel track application if I had time. So as the priority task, it was decided to implement, to create and implement a function sync-grid threads that synchronizes the whole grid. So no sub-block synchronization for now, only the whole grid. It's the most important. A few new functions were created. First, exec cooperative to execute cooperative kernels, because for CUDA API, cooperative and non-cooperative kernels are different. Some features are disabled for cooperative kernels, some are enabled, like cooperative groups. Also, it only supports up to some specified number of blocks for those cooperative kernels, so we need a function to somehow query that number as get max active blocks, and then a function to synchronize the whole grid. That's sync grid threads. During my work time, I have implemented all of those functions for the following APIs: NVIDIA CUDA, AMD HEP, OpenMP, CPU API, SED Threads CPU, and also the CPU sequential accelerator that just there for debugging. It's just sequential, no multi-threading, just sequentially executing all the functions. And for now, the Intel TBB and SQL libraries, that's for CPU and GPUs, are still work in progress. They're still not done. There are some problems with them. Specifically, SQL is just this whole functionality is considered experimental, and as far as I understand, it doesn't actually work. And the functions exist in the API but don't do anything. And also, just calling them is a huge pain, and it's for now not implemented, but I'm still working on it. Overall, I quite liked working on this project. It's like this whole high performance computing thing with a bunch of different APIs was interesting, highly educational, and I thank my mentors for their guidance, and also the whole Alpaka team, which helped me with my work. Thank you for your attention.
Thank you, Michael. Any questions? No questions. Some applause. Oh, we have a hand raised.
Yeah, hi. Not really a question. I'm Mykhail's mentor. I just wanted to thank him for the work, because when we were deciding on the topic, we knew that this was a very challenging task, and we are very happy with his work. Just wanted to say that. So thank you.
Oh, great. No, we're happy to
My
hear.
pleasure.
We're happy to hear it was a positive experience for both of you. So that's what we hope for. So, all right. Nice talk, Michael.
Thank you.
Next up is Viktoriia.
So, hi, my name is Viktoriia. And today I'd like to present the project Embed software application for a RISC-V system on chip for a Large Hadron Collider Velo detector. My mentors are Alessandro Caratelli and Marco Andorno Cern. So, as the complexity and scale ISIC designs continue to grow, we are moving towards abstract designs methodologies that enhance modularity and programmability. Our current focus is on integrating system-on-chip SoC techniques to efficiently consolidate multiple functions onto a single chip while enabling programmability in detectors ISICs. In frame of this project, we developed a technological concept how to interact with hardware abstraction layer, HAL, of the tree-glove microcontroller using C++ coding. A SoC may include a microcontroller as one of the components, but usually integrates it with advanced peripherals. Microcontrollers are usually designed for special embedded applications. tree-glove is an ISIC SoC demonstrator to evaluate the integration of a programmable system into high radiation environment for HEP experiments. It's based on open source RISC-V architecture. It's a single IBEX CPU core. Some common peripherals are included in the design. It's very easy to add an additional peripheral without the need of touching very low code. Design is built for SoCmake, which is CMake-based build system for hardware designs. The dependencies and IP blocks are automatically built and fetched with the inbuilt package manager. As a result, the installation process is really simple. About peripherals. The UART is used to send and receive serial data between a device and a computer. It does not need to separate clock signal to synchronize with the external device. Other one is the PLI. Module is designed to manage interrupts from the peripherals and can notify multiple blocks. And the last one, the timer, provides a configurable number of 64 bits counter incremented by a step value whenever the prescaler times out. Each timer generates an interrupt if the counter reaches a programmed threshold. Aimed at automating the generation of SoC hardware descriptions and software stacks, we consider user expansion of programmability options using C++ code. And here we used low-level logical operations for bits and binary shift to read-write values in the registers that configure GPIOs in our system. This runs fast on the RISC-V architecture. Also, since the HAL is a driver level which takes care of peripherals, interrupts, and installations, it has some runtime overhead in compressions with raw registers, addresses, and offsets. Therefore, our goal was to research and, if necessary, replace some routines with our own C++ code. If some HAL functions do not work out of our project, our team designs the hardware from scratch. Therefore, we have rather profound reference. HAL basic functions for GPIO, it's read pin, write, toggle pin, lock pin, RQ handler. And for our tasks with the UART peripherals, we access the UART API from HAL, which goes to the UART peripheral inside the microcontroller, where we can perform tasks like TX, RX, and others. In our C++ code, we used to swap the TX pin from 1 to 0. Can you hear me? Because just the messages appeared that my microphone does not work.
No, it works. I can hear you.
Okay. So also a special function can handle this using a counter to calculate it based on time period specified in milliseconds. Also, the configuration registers allow selection of the GPIO in input bit equal to 0 or output bit equal to 1 mode by setting appropriate bits in the register. In this case, GPIO pins can be configured to be in or output, be enabled or disabled. Values are readable and can be optionally used as interrupts. And the last one is output values are readable or readable. It's crucial to get information about workability of registers all the time to ensure they are functionally properly despite of radiation in the collider. And hence, we've created a special function to measure GPIO relays to read-write cycles for ongoing evaluation and user hardware optimization. Hopefully, it can be accelerate design process of the SOC automation and slightly improve the project pipeline. A conceptual prototype may be user-enhanced to work with calibration routines and different monitoring components in the currently designed Triglav microcontroller and efficiently integrated in future to ISIG for the Large Hadron Collider Velo detector. Thank you.
Thank you, Viktoriia. Any questions or comments for Viktoriia?
I have a question. What software stack did you use to engineer your microcontroller?
What would use missed first word? What I used?
What? Yeah, I think he asked what software stack you used.
Software like Microsoft.
Maybe I can help on this question.
Yeah,
So
please.
basically, yeah. So basically, I mean, the purpose of the project is actually we are developing a generator for this, mostly for the hardware, mostly to generate the Verilog because this custom microcontroller and the custom peripherals and so on, they're meant to go inside the ASICs that are used in basically to bring programmability inside the chips that goes inside the detector, mostly inside pixel chips. So most of the software, I mean, is all based on the RISC-V instruction set, but most of the components are custom part of this generator to be because the purpose of the project is to make a very small in terms of area consumption and so on hardware. So that's why it's a custom hardware and radiation tolerant in order to put it inside the phantom chips. So most of the software stack is actually customly done in our team. But I mean, the compiler is compiling according to the RISC-V instruction set and so on, with some custom extensions.
Do I understand correctly? It was a custom C++ software stack to compile into Verilog. Yeah?
Yeah.
Yes,
Okay.
exactly. So basically to generate the Verilog and then on top, for instance, the code that Viktoriia is was writing and so on, it runs on top of this custom hardware that we are developing.
Okay, thank you.
So the purpose of the project is actually not only to develop the custom hardware, but to develop a generator for this custom hardware based on some high-level description files in order to optimize the hardware specifically for the functionality needed inside the detector, but in a minimum area, minimum power consumption way.
Okay. Any other questions or comments? All right. Thank you. Up next is Nishank. Nishank, here, go ahead and share your screen.
Hi. Okay. Before I just get started, I just wanted to mention, I just really wanted to thank everyone that helped me in this project. So, Annalena, Nicole, Lucas, and Michael, they've been unbelievably and unbelievably helpful. That was poor word choice. unbelievably helpful and basically helping me understand like jets, helping me learn jacks. They've been so nice and supportive, and I really couldn't have done any of this without them. They've been so supportive, helping me throughout this whole summer. So I just really wanted to thank them before I started my presentation. But yeah, let's get started then. I did my project on differentiable jet clustering, and I just recently graduated from UC Berkeley, and I'm in Cambridge. So yeah, basically, let's talk a little bit about why this project is important. This is like big overarching challenges. It's called the Analysis Grand Challenge, and part of it is to create this end-to-end differentiable pipeline for high energy physics and data analysis. So let's take a look at like a general data analysis pipeline, right? So maybe you'll have collision simulation for the LHC stuff. So collision simulation, and you can do that via Geant. You can get data, and then from there you'll make these kind of cuts. So like maybe you have PT cuts, you have rapidity cuts, you have all these other small cuts you make, and then from there you'll create these observables with this data, and then from there you'll pass that through a model. So that could be like a maximum likelihood estimate, or regression, some sort of fit, etc. And then from there you get a test statistic, so something like a likelihood ratio or any form of test statistic, and you use that to test your hypothesis. So maybe it'll be your null hypothesis compared to something, and then from there you'll get your p-values, these results. You basically get these limits and final results. That's like basically your end goal. But the idea is basically, okay, inside of all this, what can we optimize basically? So like maybe if we take a look at steps 3 and 4, maybe we can optimize these cuts. Like maybe we can make a PT cut a specific area, or maybe we can make some sort of distribution cut, or maybe we can optimize these observables by parameterizing them and making them multivariate, and then seeing what happens when we vary these parameters. Can we optimize this? Right? Maybe we can optimize detectors even. But in our case, what we're focusing on is differentiable jet clustering. So yeah, we can try to optimize this observable. In our case, the observable is the jet, and we can parameterize that via the radius and optimize that. Of course, there's also other parameters, but right now we're going to focus on the radius. So we know why we want to focus on differentiable jet clustering. Now let's talk a little bit about jet clustering. So what is a jet, right? Formally, a jet's a column-radius array of particles, but what does that really mean, right? So let's imagine we have a collision simulation. So let's have two particles moving towards one another. They collide, and this produces unstable particles, which then decay. Those produce potentially unstable particles, further decay. You have this huge cascade of decays, right? And in the end, what you end up seeing is this final hit in our detector, right? So everything gets logged as hits in your detector. And the question becomes, okay, well, what really is our jet? So basically, our jet is going to consist of all of the particles that decayed from the same original particle. So what does that mean, right? That's a little complicated, right? So let's look at the left side. You see all these particles on the left, they all decayed from this one particle. See all the particles on the right, they all decayed from this one particle. We know that visually, these will be our jets, right? So the idea is now we want to iteratively combine our particles that decayed from the same original particle, right? So how do we do this? It's this process called jet clustering. So right here we have this distance metric. So this doesn't matter as much. These are just some formulas, but basically these distance metrics help you understand the distances between your particles. It's a metric for that. So now let's consider this 3-particle case. We have, let's say, a particle 0, 1, and 2. They have specific PTs and they have specific rapidities, right? So now we can use that distance formula on these particles and create this distance matrix, right? This distance matrix tells you how close together or far apart these particles are from one another, right? And in our case, what we want to do is we want to combine the particles that are closest to one another, because those likely came from the same decay or decayed from the same particle, right? So in our case, if you look at 0 and 1, emerging particles 0 and 1, we see that those have the lowest distance. And so we're going to merge the particles that are closest together. So this is traditional anti-KT jet clustering, and then you'll go on and continue to do this. So if you cluster this, you'll cluster all the particles that are closest to one another, and you'll keep going and going and going until you get these two bigger jets, right? These jets, the reason I put those little Qs there are because these jets are effectively proxies for your quarks, right? So you can't necessarily study quarks directly, but you can use these jets as stand-in representations for your quarks. So let's talk about the limitations of this, right? So jet clustering normally just has one free parameter, which is just the radius, and not every jet is going to have the same radius. It's not guaranteed to have the same radius, but that's not the only issue. The issue is that this is non-differentiable. So there's a little bit of a hand-drawn plot on the right, so we can understand a little bit what's happening. So imagine we have 3 particles with momenta 1, 0.5, and 1. So particles 1, 2, and 3. So let's say for some radius r less than r naught, we're merging particles 1 and 2. right? And we have a merge momentum of 1.5. Then let's say we change our radius so it's a little something higher than R naught, and our distance metric now tells us, oh, we should merge particles 1 and 3, right? Now the merge PT is 2, but the problem is we get this sudden jump in our merge PT, and if we try to differentiate this, well, we can't, right? We get this delta function, which peaks at R naught, and the problem is this is non-differentiable. So now, how do we fix this, right? Okay, well, one way we can do this, and it's been done in the past, is, okay, let's make things probabilistic. So we do our same thing as before, where we get this distance matrix, right? And now what we do is we get merge probabilities based off this distance matrix, and instead of picking the minimum distance particles to merge, okay, let's probabilistically select a merge decision, right? So what do I mean by that? So what does this look like, right? So we have this distance matrix, and we convert this to a merge probability matrix. So now each of our merges, so let's say we merge particles 1 and 2, 2 and 3, 1 and 3, they each have their own associated probabilities, and we want to merge each of those with a specific probability. Now we can use this to get a gradient. So how does this fix this? Well, it kind of looks like this, right? So we had this prior graph, which is, a sudden jump. Now it switches to this probabilistic merge where, okay, let's say we get to R close to R naught. Now we're probabilistically merging either 1 and 2 or probabilistically merging either 1 and 3. So we change this from a heaviside function, the sudden jump, to a softmax, which is a lot smoother and also differentiable. So this is the benefit of this. So we've solved a little bit of the differentiability problem. Now let's talk about the other part. So we can't directly take this derivative because at the end of the day, we're still just picking two particles to merge. So this isn't directly differentiable, but we can use this thing called the score-based gradient estimator. So this score-based gradient estimator is basically going to be an approach to a sample-based approach to get your derivative, right? So the idea of this is basically, okay, you're going to slightly vary these probabilities that you have and see what impact that has on your whatever metric you're trying to specifically check. So if in our case it was like the derivative of the merge PT, then we would want to see what that is. We want to see how that varies, right? So if we look at this formula itself, L of R is basically a loss function, which is basically guiding you to tell you how well your jet is clustered, and this log P of N of R, this P of N of R specifically, is your merge probability, right? So in traditional anti-KT, basically you're just going to merge two particles based on how close they are together. But in probabilistic anti-KT, or differentiable in this case, right, what you're doing is when you change the radius, you smoothly vary this probability distribution, and as a result, that's differentiable, and thus we can compute it via this score-based approach. So let's talk a little bit about this applicability in like a three-particle toy example. So this is the same example that we had before in the top right, and we want to study the first merge behavior. So the very first merge that we do, right? And right now what we're going to do is take the merge PT as a proxy for the loss function. So the prior equation where we had L of R, we're going to replace that with the merge PT. So what do I mean by merge PT? Okay, well, we sample like 10,000 times, let's say, and each time we either choose to maybe sample combine particles 1 and 2, maybe we choose to combine particles 2 and 3, maybe we choose to combine 1 and 3, right? So we have all these different decisions that we can make. And if we combine particles 1 and 2, we have the PT of those two combined. If we combine 1 and 3, we have the PT of those two combined, et cetera, et cetera. And so the expected merge PT, which is going to be this cyan plot or cyan line, is just going to be the average of that value for a specific radius, right? And then there's two other plots, which is going to be the gradient of this, right? So in our case, if we look at the gradient, we have the analytical gradient, which is basically our paper and pencil derivation of, okay, we did all the math. Okay, this is what the gradient should approximately be. And then your score-based gradient estimator, which is an actual approximation of your gradient, which is done by sampling, right? And we went over that in the prior slide. Yeah, so in this case, we see that our gradients tend to plateau to 0, which is because our expected merge PT plateaus at higher radius. So this is relevant because then we notice that, okay, for larger and larger radius, okay, that means that we're merging these two particles, the two highest PT particles. That's basically what happens, and that's why this tends to plateau. So if you look at this, these error bounds are kind of big, right? Like 50 error, that's kind of huge. But we can try and reduce that. So one thing we can do is the baseline variance reduction. So by adding this baseline, we can basically shift our loss function, so this L of R was our merge PT. We can shift that closer to 0 by subtracting away the expected merge PT. So this won't change our gradient, but what this will change is our variance. So here we can see this reduction in error on our gradient estimator, which is perfect. But things this is still relatively high, so let's try reducing this even more. So now we're going to do something called batching. Batching is basically where we average over multiple samples to reduce all these random fluctuations. So how are we doing this? We split everything into samples of 10. So let's say we take 10,000 different samples. If we split them into samples of 10 and take the mean of each of those, we now have 1,000 points, which are all closer to the mean, right? And from this, we see a reduction in variance. And boom, now we have a variance that's around like 1.5, 1.7. That's awesome. That's perfect. This is a huge reduction from 50. So now let's talk a little bit about the real particle case. Yeah. So we want to extend this to real particles. So this is an example of Pythia-generated particles. There's like 193 particles, and this is prior to making our cuts on PT, phi, etc. So after making our cuts and making a plot, this is what the gradients tend to look like for real particles. So this is the same thing that we had before, but now we did it on the real particle case, right? So in this case, we see that it seems like for very low PT, we're choosing a particle that is around PT 2.8 or so. And then as we go to higher and higher PT or higher and higher radius, we're merging it with some particle with relatively low PT, maybe 0.4 or so, 0.5, right? This is what this plot of the P merge is telling us. So is this true? Well, we can look at the cut distribution. And if we look at this, that's kind of exactly what's happening, right? So we end up merging a particle of PT 2.85 and a particle of PT 0.44. And the reasons this happens is because they're like collinear to one another, which basically means they're like effectively in the same exact direction. And so we choose to merge these two particles. And so our gradient kind of makes sense in this case. So that kind of covers our whole real particle case. And so now let's talk a little bit about what we covered, right? So we created differentiable anti-KT. We demonstrated its effectiveness on this 3 particle case, and we demonstrated on real data, and we showed that, anti-KT is non-optimizable by nature. And this basically falls in line with our end goal, which is that, okay, we want to make differentiable jet clustering as one part of our optimization pipeline. So this is just a plot to take a look at. Yeah, and this should pretty much cover my presentation. I really appreciate everyone. Thank you so much for listening. And also thank you so much to Rob and everyone in IRIS-HEP who really helped us, coordinate the presentations and helped with everything, every part of this, every step of the way. So thank you so much. I really appreciate it. Yeah.
All right. Thank you, Nishank. Any questions? Lucas?
Yeah, I don't have a question because I was a mentor. I just wanted to say, yeah, thanks to Nishank. So I think this was great. So it's a project that we've been wanting to do for a while, and I think this IRIS-HEP fellowship was a great opportunity to get started. And so, I mean, we're far from done, but I think it was a kind of a great way to get started. And also, I mean, I think it contributes to the IRIS-HEP ecosystem. So thanks, Nishank, and all the best to you. Your new position.
All right. Thank you, Lucas. Matthew?
Yeah, this is great work. So very very impressive. So as Lucas just mentioned, he mentioned that this is like not done yet, but kind of in progress. But along those lines, can you include the link to the GitHub repository in your either update your fellow profile or to include the public link or link it in the presentation for those of us who want to try and check out some of this work?
Yeah, absolutely. I'm not. I think I can double check. I don't know if the repo is public or private right now, but I can double check. But yeah, I got you. I think it might be private. But I'll do that. Absolutely, yes.
Okay, yeah. Just it's whenever it can be made, or if it is private, if it can be made public, that'd be great. Given that we want all work that is supported by IRIS-HEP to be public.
Yeah.
Yeah. So we'll just discuss it in our group. So I think, yeah, I mean, to make it public, I think we need to clean it up a little bit. But yeah, I mean, I think that's definitely the goal.
Okay. Yeah.
Jordan.
Just a random comment, but you mentioned there's a metric for that, and I'd love that phrase, and I'm stealing that, so thank you.
Thank you.
whole there's an app for that, but for particle physics theory and devs.
Yeah. It was actually Nicole who mentioned to say that. So, yeah.
All right. Thank you to all the fellows, presentations. Thank you to the mentors. Thanks to everybody else for joining us. There's another round of them next week, which I'll announce. So, and that's it for today. So, thank you.